So here's a lesson I haven't taught in 4 years because the previous classes have all met their goal of at least half passing. So I'm going to be rusty on this. This is an ellipse. Reading through the definition is a set of all points Q for which the sum of the distance to two fixed points called the foci is a constant K. So this distance here plus this distance would be the same as this distance and that distance. Those distances are always the same. That's kind of cool to some degree. But anyways, the major axis is the line that passes through the foci. The vertices are the points which intercept the major axes. So like this is a vertex, and this is a vertex, and that's a vertex. And the major axis is always the long axis. It's the long one. Anyways, they got some concepts here. The length is the length of the line segment between the vertices. The center is the midpoint between the vertices, dead center of the ellipse. You have what's called a minor axis. It's the short axis. And stuff like that. That's the vocab on ellipse. Here we have our equations. They're a lot like circles, believe it or not, because they look like circles. And we'll probably refer to this for a while because I haven't done this in several years, so I'm going to be rusty on it. All right, what do we have here? We have put the equation of the ellipse 9x squared plus y squared equals 9 in standard form. So standard form is going to be x squared over a squared plus y squared over b squared equals 1. Depending on which one's the major axis, but it really doesn't really matter. Let's see here. So the first thing to get this thing in standard form is to get it equal to a 1. It's not supposed to equal 9, it's supposed to equal 1, right? See that 1? So we're just going to divide out that 9. And we're going to get x squared over a 1 plus y squared over a 9 equal to 1. Now, let's look at a lineup process here. We'll do it as your book does it. This one is vertically oriented. This is bigger. It's under Y. This is a vertical ellipse. It's going to look something like this. Now, because it's vertical, a squared is 9. And b squared is 1. So a is going to be plus or minus 3, and b is going to be plus or minus 1. Okay, what good does that tell me? Okay, well, if this thing is centered at the origin, which it is, because it's in the form of things that are centered at the origin, see, centered at the origin, it's telling me how far to go out on the major axis. And again, this thing is vertical, so the major axis is the y-axis. We're going to go out 1, 2, 3, put an endpoint. 1, 2, 3, put an endpoint. And on the minor axis, we're only going to go out 1 unit each way. So we have found the major and minor endpoints, or vertices here. And there's my ellipse. All right, so they want us to find the vertices, the minor axis endpoints, the length of the major axis, and the length of the minor axis. And sketch the graph and check using the utility. So here is a major endpoint. It's at 0, 3. Here's another one at 0, negative 3. On the minor axis, we're at 1, 0, and we're at negative 1, 0. And that's everything they asked us to do. Okay? I'm not going to check it with the graphing utility because I don't want this video to take a whole lot of time. All right, moving forward. Find the standard form of an equation for ellipse centered at 0, 0 with a horizontal major axis length of 28. Notice it says horizontal major axis length of 28 and a minor axis length of 16. Now, graphing these is kind of optional, but it lets you see it. It's centered at 0, 0. The major axis has a length of 18, and it's horizontal, okay? Which means we're going to go back 14 units. We're going to go right 14 units. The minor axis has a minor axis length of 8, so we're going to go up 8 and we're going to go down 8. Now, the only reason I'm doing this is so that you can actually see, and maybe you're good enough at picturing this in your mind, but this is a horizontal groove. It's a horizontal ellipse, which means that it's in the form x squared over a squared plus y squared over b squared, and that's equal to 1. Now, a is the major axis radius, okay? B is the minor axis radius. So, A here is going to be 14 because that's the radius here. Ellipses actually have two radii. So it's x squared over 14 squared plus y squared over 8 squared equals 1. And you just do your squaring. It's x squared over 196 plus y squared over 64. And they both equal 1. There you go. That's how hard it really is to write an equation of ellipse if it's centered at the origin. Again, I'm a little rusty on this, so forgive me if I make any mistakes. Find the standard form of the equation of the ellipse graphed here. Shouldn't be too hard. Your major radii, A, is going to be 4. Your minor radii, B, is 2. So x squared over 4 squared plus y squared over 2 squared is 1. We're going to have x squared over 16 plus y squared over 4 is 1. And that's standard form, STD form. Moving forward. We are centered now at HK. And don't be surprised by what's going on. By the way, we're gonna talk about some of this stuff here in just a minute. Okay, the foci is coming up pretty soon. But it's exactly the same as it has been. X minus h squared plus y minus k squared. In this case, we're just over an a squared and a b squared, or vice versa, depending on where the major axis is. Put the equation of the ellipse, x squared plus 2x plus 4y squared minus 24y minus 33 equals in standard form. So what we're going to have to do is we're going to have to do the technique called complete the square. That's what we have to do. We have to complete the square. It's not going to be a whole lot of fun. We're going to do it. We're going to group our x's together. I'm going to take half of 2, and I'm going to get a 1. I'm going to square that 1, I'm going to get a 1, and I'm going to add it to both sides. Looking at the y, oh, that is a mistake. Forgive me. I have not done this right. Oops. Very first thing I'm going to do is I'm going to divide everything by 4. This one's kind of ugly. It's got some fractions. Hopefully it clears itself out. This has to be y squared. So this becomes x squared over... I'm not going to do that here. There's a way to make this one easier. So this one completed the square quite nicely. The next one does not. By the way, this becomes x plus 1 squared times x plus 1. This one I'm going to do some work. I pulled that 4, and there's a reason I didn't do it in the beginning, because it would have made factoring x squared plus 2x really, really hard to do with complete the square. Now I'm going to divide by 4. This is x plus 1 quantity squared. I'm going to divide this 4 here, here, and here. I'm going to divide the 4 there. That's going to make this y squared minus 6y, and it's going to equal negative 8. Now I'm going to complete the square. I'm going to take half of 6, I'm going to get negative 3. I'm going to take a negative 3, square it and get 9. And I'm going to add it to the left, and I'm going to add it to the right. And there is the 1 that I wanted, because they all equal 1, right? And y squared minus 6y is y minus 3 times y minus 3, which is y minus 3 quantity squared. There you go, boys and girls. There is the equation of the ellipse. Now, I'm supposed to find some things. It is in standard form. I'm supposed to find the vertices, the minor axis endpoints, the length of the major axis, and the length of the minor axis. Sketch the graph. All right, so this particular guy is centered at -1, 3. Back 1, rise 3. Puts me right there. A squared is 4, so A is 2. That's the major axis. By the way, this guy's over and understood 1. So B squared is 1, which means B is plus or minus 1. So on the major axis here, which is horizontal because it's with X, I've got to go left 2, and I've got to go right 2. On the vertical axis, B, I go up 1 and down 1. And there is my ellipse. So where are my endpoints? That's why I like to actually graph these things. I have an endpoint at -3, 3. I have an endpoint at -1, 4. I have an endpoint at 1, 3, and I have an endpoint at -1, 2. You talk about the length of the major axis. This thing is 4 units long. The length of the minor axis, it is 2 units long. 2 units. All right, find the standard form of an equation for ellipse centered at -2, 1 with the vertex at -2, 4 passing through the point 0, 1. And good test takers will draw. We are centered at -2, +1. We have a vertex at -2, 4. And we pass through the point 0, 1. They didn't really give you a whole lot, did they? They really did not. But we passed through that point. So, if I have an endpoint 3 units above, I have to have an endpoint 3 units below. And your ellipses, they have symmetry, right? So if I have something 2 to the right, I have something 2 to the left. Symmetry, kids. There's what my ellipse looks like. Now, what did I just learn? I learned that it is a vertical ellipse. Okay? So it's going to be in the form x minus h squared over b squared plus y minus k squared over a squared. Because it wasn't centered at the origin, I have to use this h and k notation. That's going to equal 1. And a here is 3. Yeah, a is 3. And b here is 2. I get hk from the center, so I am x plus 2 quantity squared over a 2 squared plus y minus 1 quantity squared over a 3 squared, and that equals 1. And of course what you do is you say that's 4 and say that's 9. Really not that hard to write an equation of a graph. We haven't got to the difficult stuff yet. We haven't. It does get rougher. A bridge over a river is supported by a single semi-elliptical arc. So you've probably seen bridges like this. A lot of bridges are like this. You've got a roadway, you got some water, you got your river underneath. It's kind of looking like an angry face right now. But the bridge itself is an arc, okay? It's half of an ellipse. All right, let's see what we can do here. The river is 50 feet wide, so I guess what they're telling us here is that the bridge is going to be 50 foot wide. At the center, I did this diagram wrong, forgive me. Let me erase this. I didn't read all the text. The bridge is supported, okay. The roadway is 4 feet above the center of the arc. All right, Milbrath, you should have read the text. The bridge is supported by the ellipse, okay? That's not perfect, but it's a whole lot better than what I had. The river is 50 feet wide, which means that the roadway is going to be 50 feet wide. At the center, the arch rises 20 feet above the river. Okay, that's good information to know. This is 20. No, I still don't have my arch right. this is what I want. At the center, the arch rises 20 feet above the river. The roadway is 4 feet above the center of the arch. So there's 4 foot here. Now, this is such a weird diagram. The way they're saying this, the roadway is 4 feet above the arch. Give me a second to think on my diagram here. Okay, so my time's up. And yeah, I just completely borked this thing. You can tell I've never built a bridge, huh? I was trying to make it make sense. It looks like that. Because, you know, I'm an idiot, and I know that's what it looks like. I know that's what it looks like. I've seen bridges before. Anyways, to the arch, it's 20 foot. And there's 4 feet from the bottom of the arch to the roadway. That's the diagram I need. Stupid Milbrath. All right, what are we supposed to do here? What is the vertical distance between the roadway and the arch 15 feet from the center? Okay. We need to find a good place to make this thing centered. So what I'm doing here is I'm centering some things and I'm thinking about it. I'm going to make this the origin. We're going to center at 0, 0. And if I do that, one endpoint of my ellipse would be negative 25, 0. This one would be positive 25, 0. So I definitely know that it's a horizontal guy, okay? At the center of the arch rises 20 feet above the river. Be cool if I knew how many feet above the river this thing is. I wonder if the author is implying that it looks more like this, that this is where the water level is. I bet they are. I bet that's exactly what they're doing. So that's the only way that what I've drawn would make any sense to me. So let's make that 20 foot. That's going to make this coordinate right here 0, 20. And if we think about this down here, this would be 0, negative 20. And this would be the imaginary part of the ellipse that does not draw on it because it doesn't exist. All right, so cool. I can work with this now. I can write an equation. It's going to be x squared plus a y squared. The major radius is 25 because it was 50 feet long. The minor radius is 20, and that would equal 1. Now, what do they want us to do? What is the vertical distance between the roadway and the arch 15 feet from the center? Okay. So if I go over 15 feet from the center on the arch, on the roadway, I would be at 1524 because 20 feet and 4 makes 1524. Everything on this thing has a y value 24. The question here is, on the arch, you're 15 and what y value? And then you can find distance, right? So if I have x, I can get y. I'm going to plug my 15 in. 15 squared over 25 squared plus y squared over 20 squared is 1. And the numbers are pretty big and I'm pretty tired, but I'm just going to multiply everything by 25 squared. See what happens. 25 to the second times 15 to the second over 25 to the second. What I'm doing is I'm clearing that initial fraction. It's 225. All right, I distribute to the second guy. The question is, what's 25 squared divided by 20 squared? So I get 25/16 y squared. And that's going to equal to 25 squared, which I really hope is 625, or I just shouldn't be doing math today. That equals 625. And I'm still going to keep clearing my fraction, okay? But one thing I can do real quick is I can subtract that, and that would have me at 25y squared equals 400. And I forgot about the 16. So then I can 16 both sides, and I'll get 6,400. 25y squared equals 6,400. And lastly, divide out the 25. Appreciate that the author of this question chose things that give you nice numbers, and I get 256. Y squared is 256. So y is going to be plus or minus 16. So whether I'm here or here, which would have been technically negative 15, 24, I'm going to have the ordered pair 15, negative 16, or I'm going to have 15, positive 16. Whew. A lot of work for this little problem. Those guys are 8 foot apart, because 24 minus 16 is 8. All right, we got like 4 to go. The foci are kind of cool, and they give you like one little minor application of it, but the location of the foci can play a key role in ellipse application problems. Standing on a focus in a whispering gallery, and that is such a thing, allows you to hear someone whispering at the other focus, just whispering very quietly. You can be very far away, and you can still hear them as though they're right next to you. To find the foci, we need to find the length from the center to the foci using the equation b squared equals a squared minus c squared. So I've kind of glossed over this so far because we haven't needed it, but I told you it was coming. It's right there. It's the foci, the focus of the ellipse. It's where everything radiates to. It looks similar to, but is not the same as Pythagorean theorem. So here's one. The National Statuary Hall Whispering Chamber is an elliptical room that is 46 feet wide and 96 feet long. To hear each other whispering, 2 people need to stand at the foci of the ellipse. Where should they stand? So let's kind of diagram this out. It's 96 feet long, which means it's going to go out 40 feet to the right. And it's going to go negative 48 to the left. And it said it was 46 feet wide, so it's going to go up to 23. And I should be saying 0, 23. And it's going to go down to 0, negative 23. Now this is what it would look like. And the question is where are the 2 foci? We usually call them foci 1 and foci 2. Where are they? Okay, that's the real question. Where are these things? So first off, it is horizontal, okay? A is 48 because it's the major axis radius. Again, that's the major axis radius. And again, I'm a little rusty on these. I kind of forgot how to teach them. I ain't taught them in over 3 years. B is 23, which is my minor axis radius. And because I chose to draw centered at the origin, I can just do x squared plus y squared equals 1. This would be over the major axis, which is 48 squared, and this is over the minor axis, which is 23 squared. But the whole point was I picked out that A was 48 and I picked out that B was 23. That's what I picked out. So you have an equation that you get to use that says B squared equals A squared minus C squared. Okay? We can feed that some stuff. So B is 23. 23 squared must equal 48 squared minus C squared. Okay? And I'm just going to do some manipulation. I'm going to move some stuff around. C squared is going to be 48 squared minus 23 squared. it's about 1775, or c squared is 1775. So c is going to be the square root of that number. It's around 42.13 feet. Now, the foci, they both lie on the x-axis, and the c is the distance from the center. So one of my foci is at, now we're just going to round on paper, 42.0, and the other one is at negative 42.0. Where should they stand? They should each stand about 42 feet from the center, or 84 feet away from each other, but they need to be 42 feet from the center is where they need to stand. All right, find the foci of the ellipse as given. The bigger number is a squared. The smaller number is b squared. So a is the root of 29 and b is 4. And remember, your formula is b squared is a squared minus c squared, right? B squared is a squared minus c squared. So, sorry, b is 2. I don't know why I wrote 4. b is 2. So 2 squared must be root 29 squared minus c squared. Of course, we already know these are 4. 4 is 29 minus c squared. Shift things around. C squared is 25 and c is 5. Now, where are the foci? I'm going to graph, because graphing is really the only way to make it obvious. This thing is centered at 2, negative 3. It has a major axis of root 29, which is, you know, a little over 5. 5.4. I don't know why I'm going that way. 1, 2, 3, 4, 5, 6. It's down about 5.4. 1, 2, 1. Where am I at? 1, 2, 3, 4, 5, 6. About right there. The minor axis is 2. And the reason I'm drawing this is because you need to understand that foci are on the major axis. Okay? So the foci are going to be plus or minus 5 from the center on the major axis. So it'll be about right there and about right there. So they're going to be at 2, 2, and 2, negative 6. 1, 2, 3, 4, 5, 6, 7, 8. 2, negative 8. What we got left? These are taking longer than I thought. I don't have a lot of time left. Find the standard form of equation for ellipse with foci at negative 1, 4 and 3, 4 and major axis length of 10. They don't really give you anything else, do they? Well, I can tell you this, that foci, they lie on the major axis. So that's going to help me. I have a foci at negative 1, 4. I have a foci at 3, 4. Okay, so this is my major axis. And my major axis has to be 10 units apart. Now, your center is the midpoint of the foci. And just go back and look at the graphs we've done. The center is the midpoint, okay? So the center is the midpoint. Cool. Here's my center. So my center is at 1, 4. Okay? Now, the major axis length is 10, which means the radius is 5. So I'm going to go over 5 units. 1, 2, 3, 4. 1, 2, 3, 4, 5. I'm going to have to go back 5. 1, 2, 3, 4, 5. Okay, so here's what I have. I know that A is 5, right? C is going to be the distance between these two things. So C is 2. And I know that b squared is a squared minus c squared. Lots of little things can be figured out. So b squared is a, which is 5, 5 squared minus c, which is 2, 2 squared. So b squared is going to be 25 minus 4, 21. b is root 21. I don't actually have to graph this, but because I have everything, all right? My center is at negative at 1, 4, so x minus 1 squared plus y minus 4 squared, because remember this is hk. This is going to be over b squared, and you know b squared is 21, and this is over a squared, which is 25, and it would equal 1. Whew. Deep stuff, huh? Last thing we get to talk about is the planetary orbits. It was long thought that planetary orbits around the sun are circular. They're not. They're like Earth is something like 99.9% circular. Like it's ridiculously close to being a circle, but it's actually an ellipse. Kepler in 1600 discovered they were elliptical. His first law of planetary motion says that planets travel around the sun in an elliptical orbit with the sun as one of the foci, and that's true. The sun's only one of the foci. The length of the major axis can be found by measuring the planet's aphelion, its greatest distance from the sun. So the aphelion here is going to be the radius of the major axis, and the perihelion, which is the minor axis radius. All right. Let me make sure I'm doing that right. Give me a second. I want to make sure I do this right. I don't want to mess this up because I just had a thought and I don't like it. Yeah, I'm glad I had that thought because I don't agree with what I just wrote. This distance is the aphelion. This distance is the perihelion. I'm probably not saying that right. I'm not an astronomer. Why? That's actually important to think about that, okay? All right, Mercury's aphelion is 35.98 million miles. So remember, we have the sun at the center. It's one of two foci. It's a focus. It's the primary one. But there's another focus over here, okay? One of your distances is going to be 28.58. And the other distance here to that same focus is going to be 35.98. Now my diagram's not really to scale. Now, if one focus is 28.58 million miles from the sun or from the orbit of the planet, so is the other one. Okay, that's important because that's allowing me to find C. I'm just going to make this thing centered at 0, 0, okay? Now, if I take my two 28.58s together, I just double them. I don't want to get anything wrong. I'm pretty sure it's 57.16, but, you know, whatever. I'm not having a math day. It's been a hard week, bruh. I get 57.16. That's how far these guys are from each other. Or sorry. And I take that away. I don't like what I just wrote there. That doesn't make a lick of sense. Or does it? What I'm wanting to figure out is I'm wanting to figure out how far apart these focuses are from the center. Okay. I know, and then this is what I do. I know the major axis length is 28.58 plus 35.98. Let's see what that yields me. 28.58 plus, and I've actually never taught this particular lesson out of this book. All the years I've done pre-calc, the kids have always met their goal. 64.56. All right, so all the way across is 64.56. If I take away the 57.16, I get 7.4, which is the distance between the foci, okay? If I divide that by 2, I discover that the foci are 3.7 million miles from the center. So I'm doing all this stuff to get some stuff. And by the way, this distance from the center is C. That is C, all right? Now, by the way, if I take the major axis of 64.56 and divide it by 2, I get its radius. So I get that A is going to be 32.28. That seems right. And I have C. So now I'm getting somewhere. And I know that B squared is A squared minus C squared. So B squared is 32.28 squared minus 3.7 squared. Fun stuff, huh? Me and Coach K were talking. We're not going to force kids into my class next year. We're going to give you an option, which is what I asked him to do a long, long time ago. This wasn't Milbrath doing this to you guys. But at the same time, I want to point out that all of you are very capable. You just chose not to do things timely. By and large, you chose. And the environment in this room was not what it needed to be. So anyways, that's A squared minus C squared. We take the square root of both sides, and this is B. B is about 32.07. Not that I actually needed it, because they just want an equation. I centered at the origin, so it's x squared plus y squared. It's going to be 1. Let's see, it was horizontal, so this is going to be 32.28 squared. This is my minor axis, 32.07 squared, and it equals 1. Good times. Enjoy that stuff. A lot of stuff going on. I just got to make you a worksheet for it.